with one of our HPC users wanting, then kindly providing a lightning talk on their use of the GPUs on the HPC after. Next slide, please. So why are we talking about GPUs today? As research has become more data intensive and AI driven, we've progressively introduced GPU capability across the national platform. We've consulted with the research community to understand their needs in this space, and we've collaborated with the research teams to help make most of these tools. Our investments initially started with GPUs nearly a decade ago when we first got the P100s, the old P100s, which we don't have anymore. Then we added some A100 PCIEs. We initially launched them just as machine learning only, so we wouldn't allow anyone who wasn't doing machine learning workloads onto those. But we've broadened them access for more general demand after that, and now they've kind of become more available just general workloads as well. And the demand has just grown, not just in machine learning, but in general demand as well for all GPUs. Then as part of our platform research and refresh in 2025, we brought on more A100s and some new H100s. And we again saw usage of these GPUs continue to grow and demand continue to increase. And now we're in the process of getting some new RTX Pro 6000 GPUs. Since we first acquired the P100 GPUs, they've been utilized, and all of our GPUs have been utilized in a wide range of research domains on the HPC. Everything from simulating infectious disease outbreaks to modeling extreme weather events to analyzing ecosystems, which you can see in some of these images up here represented. Next slide, please. The purpose of this webinar is to provide an overview of the GPUs available on Mahawika and advise current and prospective GPU users on how to get the most out of their use of the ReEN's GPUs. In pursuit of this, this webinar can broadly be broken into 4 parts. In the first part, we will outline the differences between CPUs and GPUs and detail why you might want to use GPUs in your research. We will then provide an overview of the available GPUs on Mahawika and provide advice on when you want to use each type. After which, we will offer some guidance on testing and profiling your GPU usage to ensure that you are using the optimal GPUs and getting the most out of them. Then to wrap up the webinar, Wanting will then provide a quick lightning talk on their use of the GPUs, giving you a real-world example of how someone might be making use of GPUs on the HPC. Next slide, and then that's just the next part, and the next slide again. As you can probably guess from the name, graphical processing unit, GPUs were originally created for graphics processing. Since CPUs could only work serially, they weren't very good for processing all the calculations required for displaying hundreds or thousands of pixels at the same time. The idea behind GPUs was that rather than being made up of a single, or as often the case now, a few very powerful cores, GPUs would be made up of hundreds or thousands of individually weak cores. But quantity is a quality of its own, and GPUs were highly effective at performing many simple calculations simultaneously, solving the graphics processing problem for early computer scientists. Now, decades after the first GPUs were developed, it turns out that lots of scientific problems can be effectively broken down into many mathematically simple problems. And this is only becoming more true with the explosion of machine learning, AI, as it's now often called, technologies. Next slide. But this power does not come without a cost. While a CPU is a generalized piece of hardware that can function alone and perform most functions on a computer, GPUs are highly specialized and cannot function without CPU support. Additionally, because so much of the GPU chip is taken up by cores, there's very little space for anything else. So GPUs have very little chip space devoted to control units or cache, and the cache it does have tends to be further away from the cores than on CPUs. This limits the size and access speed of data that GPUs can work on compared to a CPU. And along with their much lower clock speed, which means that GPUs have significantly worse latency than CPUs. So while GPUs are extremely powerful tools for many tasks, they are not a panacea. So it's important to understand both when you should be considering GPUs at all and what types of GPUs you should be considering and how to test if they are the right choice for your research. Next slide. However, if you can utilize GPUs in your research, there are potentially significant advantages, including, but not limited to, making your code run significantly faster, which can then allow you to proportionally scale up your models, which can allow you to research topics that were previously seemed computationally infeasible. Next slide. Now we're just on to the next section, and then next slide again. Oh yeah, cool. So what GPUs do we currently have on Mahawika? We currently have 3 types of GPUs available. The first of these are the L4s, which we have 16 of. The L4s are our least powerful GPUs, and they have 24 gigabytes of VRAM. We then have the more powerful A100 GPUs, which can be further broken down into the 40 gigabyte and the 80 gigabyte VRAM nodes, of which there are 8 and 16 respectively. And we finally have our currently most powerful, but not for long, GPUs, well, sort of, which are the H100s, which have 96 gigabytes of VRAM. We only have 8 of these right now. Next slide. But how do you decide which of these GPUs you should be using? There are 3 major factors you want to consider when deciding which GPU your work should be running on. The first of these factors is whether your code requires double precision floating point format, or FP64. Of Mahawika's GPUs, only the L4s do not have FP64. And for those of you unaware, FP64 is slower and more memory intensive than FP32 or FP16, but allows for more decimal places and calculations, making it significantly more accurate and consistent, which can be integral for many scientific softwares, especially those doing physical simulations, commonly found in physics and chemistry. However, for things like machine learning, such precision is generally unnecessary. So if your work doesn't require FP64, you may be able to consider running on the L4s instead of any of the other GPUs. Next slide. Cool. The second factor to consider is VRAM. This is the memory directly associated with the GPU for performing tasks. Your jobs will require both CPU memory and VRAM for the GPU to function. If your jobs can function with less than 24 gigabytes of VRAM and do not require FP64, as mentioned in the previous slide or the previous section, then the L4 CPUs, again, may be right for you. But if you require more than 24 gigabytes of RAM, so between 24 and 80 gigabytes of VRAM, you'll at least need to use the A100 GPUs. And if you require greater than 80 gigabytes of VRAM, you're going to have to move on to the H100s. And then next slide. Cool. The final major factor you'll need to consider is compute power. The L4s, as I mentioned, are less computationally powerful than the A100s, which are in turn less computationally powerful than the H100s. But not all jobs can effectively utilize the extra computational power. So you'll need to test whether you can make use of it, which we'll cover how to do later in this webinar. There is no hard set rule on how much performance increase you should aim for when moving from the L4s to the A100s to the H100s. But in terms of compute allocations, we value the A100 hour as being about 6 times the value of a L4 GPU hour, and we value the H100 hour as being about 10 times the value of an L4 GPU hour at this time. So that's a kind of good rule of thumb to think about performance-wise that you should aim for, is maybe getting 6 times performance moving to the A100s or 10 times performance moving to the H100s. 2 other minor factors worth noting are, one, that the L4 GPUs do not have NVLink, which is high-speed GPU to GPU communication, instead relying on CPUs for their GPU to GPU communication. This means that if you're using multiple GPUs, you will experience increased latency between the L4 GPUs than if you're using the A100s or the H100s, which do have NVLink, meaning the GPUs can communicate directly with each other. And 2, the 80 gigabyte A100 GPUs are migrated from the older HPC, so they have the older Milan CPU hardware architecture. So while most GPU jobs do not have a large CPU component, if your GPU jobs do have a significant CPU-bound component, you may notice reduced performance on the 80 gigabyte A100s compared to the 40 gigabyte A100s. At the general rule, you should attempt to split out the CPU portion of your task as much as possible, though, with the GPU jobs, in order to minimize the idle GPU time when processing the CPU-bound tasks. But the difference between the A100s and the CPU architecture is just another reason why you want to be conscientious of this. Though in saying this, we are in the process of acquiring some brand new RTX Pro 6000 GPUs, as I mentioned, which will replace the 40 gigabyte A100 GPUs. And so you won't really need to think too much about the difference between the 2 A100s in the future. And these new RTX Pros are kind of a step up in many respects from the H100s, though not one for one quite. Next slide. So to summarize, before you request a GPU, you should consider whether your job requires FP64, how much VRAM your job needs, how powerful of a GPU your job requires, and whether your jobs have a significant portion of CPU-bound tasks. Also, whether your job's CPU-bound portion can be split out into other jobs to reduce idle time. One more thing to be aware of is that different GPUs also have different levels of demand and utilization. Currently, the H100s and the A100s are pretty flat out most of the time, but the L4s have much more significant amount of relatively quiet time. So jobs currently are queuing for 1 to 3 days on the H100 and the A100s, but they're only queuing for often less than 1 day on the L4s. So if your jobs can run on the L4s, it's worth considering moving them there. And so another reason why you want to make sure you're, testing which job GPU is optimal for you, because sure, you may get a little bit speed up going to the A100s or the H100s, but if it's not a significant amount, you may end up waiting longer if you've run them all there rather than the L4s because the queue times are much longer. I will now hand over to my colleague Jeff, who will go into more detail about how you might be able to find answers to which GPUs you might want to use when.
Cool, thank you, Anthony. So we'll talk now about trying to get the most out of your GPU. So talking specifically about utilization, testing, and profiling. So first, let's talk about checking your job's GPU utilization. So it's really important to understand if your job is how your job is using the GPUs, because sometimes jobs can not use the GPUs effectively. Potentially, sometimes jobs can fail to actually run the GPUs in the first place, which means that the GPU was never utilized in the first place. Jobs can sometimes use a little amount of GPU memory, but be running on a large memory GPU. Or they might not utilize the GPU very well in terms that it's not actually using the full potential of the GPU. So it's really important to be doing checking and testing to make sure that your jobs are using the GPUs effectively. In particular, what we're going to talk about today is how you can perform some very simple 15-minute test jobs to check that your job is actually using GPUs, as well as using the correct GPU for your job based on your GPU efficiency, utilization, and memory consumption. So let's first talk about how you can do a simple 15-minute check of your jobs to understand how they're using the GPUs. So in this case, what we're going to do is we're going to look through how you would actually set up this job and how you would actually monitor the amount of how the GPU is running. So the first thing to do is to add GPUs to your Slurm configuration. Specifically, you want to add your GPU per node equals the GPU, and in this case, looking at 1. In this case, we'll be using L4 as an example. You then also want to use this QoS equals debug, which allows you to get onto the queue, up the priority of the queue, which means your job will get on much quicker. But we limit this to 15 minutes testing maximum. So you can request 15 minutes on QoS equals debug, but nothing more. You then want to write the rest of your Slurm submit script, and then submit it to Slurm as you would usually do, and then wait until it's run. Once you've run the job, you'll find that you can actually get information about the job by typing into the terminal Ceph and then the job ID that was given back. You should have been able to get this job ID when you submitted SBatch in the first place, and it would have come up with a job ID for you. When you run this, you'll get a little thing pop up in the terminal that looks a little bit like this. And in particular, you'll be looking at these 5 components that specify your utilization in the memory of your job. In particular, for GPUs, we have GPU utilization as well as GPU memory. And this can tell you a lot about the utilization of the GPU, how much it was actually utilized, as well as how much memory was used. You can also perform a slightly more detailed 15-minute test job to check how your job ran over time. So the way to do this is to to write your Slurm script as you would usually do, including those 3 lines, time, GPU per node, and QoS equals debug as before. But you also want to include these 2 lines, which is sbatch profile equals task and account G frequency equals 1. You then want to write out your Slurm script as you did before, and submit it as a job. Once you've done that, you will have noticed that again it would have you would have printed out the job ID for this job. And once you've done this, you want to wait for your job to finish. Once it finishes, you want to run the following command, which is profile underscore plot job ID. What this will do is it will make a plot, which is called job ID underscore profile.png, which can tell you about how your job functioned or how it ran on the GPU over time. Depending on what operating system you use, can sort of change how you might want to see it. But in many cases, you'll want to download this to your computer to view it. However, if you're running a Mac or a Linux, you can also use this short little command gm display job ID underscore profile.png, which if you're running on X11 will just pop up. And what you'll see is something that looks a little bit like this, which will include information about the GPU's utilization over time, as well as the GPU memory. So in this case, for example, this would tell us that our GPU consistently used 500 megabytes of VRAM over time. But interestingly enough, you can see that the utilization of the GPU changed over time, initially starting at 0.4, which was 40%, and then dropping down to maybe about 0.3 or 30%. So this can help you sort of profile what is happening with your job over time. In particular, you can use the time down here, which is the time that the job ran. So i.e. at this job ran at 12:09 p.m., up to 12:23. And you can compare that with logs to figure out what your job was actually doing and compare that with the amount of utilization that the GPU was being utilized for during that time. And there's that. So now what I'm going to show you is a little guide for how you can determine which GPU is best for your job. You'll find that there's actually quite a lot of information here, so I recommend not worrying about taking in everything right at this moment. Again, as Nisha said, we'll have this recorded and will be up on YouTube at some point, so you can review this later on. And also, all of this advice is given in our documentation. So all of the flow chart that I'm going to be showing here will all be presented online in our documentation. So let's begin. What you want to do first when you've got a job that you want to run on the GPU is you first want to run a 15-minute test job on the L4s. Then you want to ask yourself, once you've run that job, did the job crash because it didn't have enough GPU memory? In this case, you'll need to upgrade the GPU that you use to something that has a bit more memory. In this case, you'd want to go next to the 40 gigabytes A100 card. The next thing that you want to figure out is using those little 15-minute tests that we did before, using the information that we looked at before, you want to figure out, did your job only utilize 0% of the GPU, i.e. did it utilize the GPU or not? If it didn't utilize the GPU, you might want to go back and check that your program can actually run on the GPUs or check for issues that your program might be having regarding the GPUs, particularly during that 15 minutes. If you get past those two things, you then want to understand how long your job is actually going to run for. And this is partially because we've only got our GPUs are in quite high demand. So if you know that your job is only going to take an hour or 2 hours to run on the L4s, and you might want to consider how far your job actually got through in that 15 minutes and compare that with how long you think it will take in total. If you think it's only going to take an hour or 2 hours to run, you might as well just use the L4s and yeah, use the L4s because that will have the least waiting time. Otherwise, if you get to that point and you find that all of that you pass all of those you want to continue doing testing, what you want to do is record the GPU utilization and memory that you used, as well as the number of steps that your algorithm took. And this is a little bit based on what your work is. Steps might mean how far in the machine learning process that you got to, or for example, if you're looking at physical simulations, it might be how many steps or how many iterations that your job ran for and up to those 15 minutes. You then want to take that information and repeat the same process on the A100s, starting with the 40 gigabyte card. And again, you want to ask yourself the next few questions. The first thing is, did your job crash again because it didn't have enough GPU memory? In which case you'll need to upgrade and look at using a card that has a bit more memory on it. Then you want to ask yourself the following question. Compared to the L4, did your job utilize the GPU better, or did your algorithm run faster on the A100 compared to the L4? If you find no, the L4 was actually utilized your job better or it ran faster, then the L4 is the one to use. However, if you found that that your job did run faster on the A100, or it was utilized better on the A100, then you want to keep going through this flow diagram to figure out is the A100 for you or not. We then go on and repeat the same process for the H100. So hopefully you're getting sort of the gist of what you want to do. As you start with the lower performing cards, you want to keep testing on the higher performing cards and higher performing cards until you find the sweet spot. So just finishing off, you want to then run, if you get to this point and you want to run a 15-minute job on the H100, you then want to ask yourself the question again, did your job utilize the GPU better, or did your algorithm run faster on the H100 compared to the A100? Again, if you found the A100 was better, you want to stick with the A100. If you found that the H100 was better for you, then you want to consider using the H100. Again, this is a little bit flexible based on what you consider as being better, because you want to think about, is it better for the amount of cost that you might be using, which Anthony was talking about before. But again, this gives you a guideline of roughly what you might want to consider. As well as this, as Anthony was saying, we're getting some new GPU cards, specifically the RTX Pro 6000s will be added. And these are particularly ideal for doing machine learning, particularly for training, because they have quite a lot of memory on them. So we'll update this flow diagram as we get those cards in, and we'll update the GPU documentation once we have those new cards in. So essentially, this is a watch this space to see what our guidelines are for when we get those new RTX Pro 6000s and how you can use them effectively and efficiently for your work. So now with that, I'll hand over to Wanting, who can tell us a little bit about her work.
Thank you. Hi, everyone. My name is Wan Ting. I'm a computational biochemist from the Ferrier Research Institute at Victoria University of Wellington. My research involves studying proteins and enzymes using computational methods. And one of these methods is molecular dynamic simulations. As you in the picture on the left here is a typical setup of a simulation I would do. So in this kind of simulation, we have to put the protein molecule inside a box filled with explicit water molecules and ions, which means the system here can include a large number of atoms. So typical one like this one, it contains more than 100,000 atoms. So this means that they have to naturally be run on HPCs. And I've had experience being a long-time user using both the CPUs and GPUs on NESI. And today I'll just share a couple of thoughts and perspectives purely as an end user. So one thing to consider when I moved on to GPUs is actually how compatible the software I'm using to the GPUs. So personally, because the software I use, NAMD, is already pre-compiled, so I'm actually limited to what this software is written to be run on. So for NAMD, in the early days from 2013 to 2020, the version number 2 was written to purely work on CPUs by speeds up the simulation by parallelizing over multiple nodes of CPUs. And then in the early 2020s, I think NAMD started to develop versions that can be run on GPUs. And I only started using the GPUs from version 2.13 on NESI from 2020. And at the time, I think running on the GPUs provided some acceleration on the simulation speed, approximately double the speed in my own experience for the system I was working on at the time, compared to running on CPUs. And then from 2024, NAMD version 3 came out, fully compatible with the GPUs. And NVIDIA did their own benchmarking, claiming it provides up to 9 times throughput with their A100 GPUs for NAMD 3. So together with the help of NESI support team, I switched to NAMD 3 from 2024 and mainly use the A100 on NESI. So I'm not an expert in computing architecture or software engineering, so I can't do much of this or any of this without the help of a lot of help from the NESI support team. During the trajectory of my user history, whenever it's time to switch to a different architecture or a different queue, I always get prompted by the support team. Really thankful for that. So the support team helped me actually compiling the codes, different versions on the platform, helped me writing the job submission scripts to tailor the setups, parameter settings, to make sure the jobs can run properly. And I worked together with the support team on several occasions to optimize the performance of NAMD on NESI. So to make sure we have the best setup to support our research, which I'm really thankful for. So as a user, if you're looking to switch to GPUs and not sure where to start, I would highly recommend getting in contact with the support team because they're always here to help. And I've had quite good experience with that. Next slide, please. Yeah, so so software compatibility is somewhat out of my control as the end user. What I thought I could control and consider is actually the speed of the simulation versus the queuing time required for on NESI. So this graph is an old benchmarking test I did back in the day when I was using NAMD version 2.13. I started to consider using GPUs. So NAMD, the software, actually gives out benchmarking information in the log file during the first few minutes of the job running. So it actually tells you, based on the current setup, how many nanoseconds of a simulation is going to go through per day. So I can use that information to benchmark different settings of the number of nodes or the CPUs or GPUs I use and compare the setup to choose the best one. So based on this graph, if I use the left block here are the CPUs. So if I use more nodes on the CPUs, the simulation will in general go faster. But requiring more nodes actually on NESI at the time or means that I actually queue for a much longer time. So I have to choose between which number of nodes I would ideally use to balance between these two. So at the time, if I were choosing, I would settle with using 15, the red highlighted bar, using 15 nodes if I was using CPU. But running on GPUs, even 1 or 2 GPUs can reproduce the speed compatible with running on across more than 10 nodes required for the CPUs. So if we look at the right-hand block with the GPU setup, ideally, of course, I'll be running on A100 because it requires only 1 GPU and it produces the fastest simulation. But I think at the time, because there were fewer A100s available and the demand for this is quite high, actually queuing for A100 is really, really long. So in contrast, the P100s at the time, the queue was largely left unused. So prompted by the NESI team, I tried out the P100s, and I at the time actually chose to use the setup of using two P100s for my simulation, which still has the reasonable speed, but also significantly reduced my queuing time
Queuing
uh,
time
to,
to
so I could get to my results faster. So these are just the two things I considered as a user when I try to switch to GPUs and different platforms, which I hope will be helpful to you. Thanks.
Cool, thank you.